Hey all you wonderful viewers out there, welcome to another Physics Calculus video. Today I have another moment of inertia integration problem for you guys because I feel like this is such an important topic. It's important that we learn to integrate physics problems well to be prepared for later physics classes. So this one is adapted from Chapter 9, Problem 54 from the university's physics textbook, and it says, use integration to find an expression for the moment of inertia of a thin rod with uniform mass distribution about an axis passing through one of its ends. The rod has total mass m and length l. Okay, a couple things to note here. First off, we have a thin rod, so that means that the width is negligible, and we have uniform mass distribution. So that means we're not going to need to integrate to find the mass distribution. It's going to be pretty easy to pull out from our diagram. So let's get started here. So let's write down the moment of inertia integration formula. So that's going to be I equals the integral of r squared dm, and we have a rod here. And the axis that's rotating about is passing through one of its ends, just like this. And it has length L, so this is x equals L over here, and x equals 0 over here. And that's going to make it really easy for us to find the limits of integration. Hold on, let me change the focus real quick. Okay, so we have our shape drawn, and yeah, so we need to integrate over the length of this rod, right? Because for each section of this rod, x is changing. We have some little part of the mass dm that we're integrating over, and this is our r. So r is changing, so it can't come out of the integral, and we're integrating with respect to dm. We're adding up all the tiny differential elements of the mass of the rod. So we're told that it has total length L and then total mass m. And that's going to be important for later. For now, though, let's figure out what dm is. So dm, in general, is a constant based on the dimension of the object you're integrating over and a tiny differential element of that dimension. So right here, it's a thin rod, so we're just integrating over the length, which means we're integrating over one dimension. We don't need to do an area integral or a volume integral or anything. So dm is going to be lambda dx because x is changing from 0 to L, x is changing. So we're integrating with respect to x, and then lambda is just convention. It's the Greek sign that we use when we're integrating with respect to one dimension for mass integral. So we can plug this expression in here, and we can switch r to x because if you'll notice, in our diagram here, r equals x because it lies on the x-axis. So r is essentially just x. So we can rewrite this as I equals the integral of x squared dx. And our limits of integration are going to be 0 to L. 0 is less than or equal to x is less than or equal to L. Because x starts at 0 and ends at L, because the length of the rod is L. So we can plug that I'm sorry, there's a lambda right here. So we can plug that in here to our integration symbol. So we have I equals the integral from 0 to L of lambda x squared dx. Alright, so if you're familiar with integration, this should be pretty straightforward. We pull lambda out of the integral because there's a uniform mass distribution. So we can pull lambda out because it's a constant. If we didn't have a uniform mass distribution, then lambda would equal some function of x, and we wouldn't be able to pull it out. We would have to plug that expression for x in for lambda and integrate over that. But the mass distribution is uniform, so we can pull it out. So this is lambda times the integral from 0 to L of x squared dx. Okay, so taking this integral, we'll just use the power rule. So this exponent increases by 1, and we divide by that new exponent. So this is lambda times 1/3 x cubed from 0 to L. Okay, so substituting ln for x and subtracting from 0 for x, which is just 0, we get lambda, 1/3 lambda L cubed. Alright, so we want to express the moment of inertia in terms of m. So we need to find a way to relate lambda and m. And for this problem, this is pretty easy because we have a uniform mass distribution. So what's lambda going to be? Well, this entire rod has total mass m, and it also has total length L. And if lambda is the mass distribution, and if the mass distribution is uniform, then it's just going to be this entire mass m divided by L, right? Because for each section of the rod, it has a mass equal to that of the total mass divided by L. So lambda equals m, the total mass, over L. So plugging that in here, we have 1/3 m over L times L cubed. So this one cancels out, and then this exponent cancels out. So what we have for the moment of inertia for this specific object is I equals 1/3 ml squared. And yeah, this is the answer. Thank you guys for joining me today. If you have any questions, please leave them in the comments down below, and I will try to respond to them. Thank you for joining me. Have a good week, guys.